In my earlier video, you understood how to install a 2-node Hadoop cluster. I have already prepared documentation for installing Hadoop in pseudo distributed mode. I am not going to show you how to install Hadoop in pseudo distributed mode because it is similar to multi-node cluster with few differences. If you follow this documentation steps one by one, you will be able to install Hadoop in pseudo distributed mode. In this video, I will discuss about some HDFS basics. Whatever I am discussing in this presentation, you might be knowing most of the concepts I have discussed in my earlier video, but let us go through these basics. You will be learning some few more things. As you understood already, Apache Hadoop is a framework that allows for distributed processing of bulk data using clusters of commodity hardware, cheap hardware, using a simple program model. If you talk about Hadoop history, it all started from 2002, where Mr. Dow Cutting and Mike Cafarella started working on a project called as Nutch in Google. So while this Dow Cutting was working on a Nutch, in 2003 Google has released a papers called as GFS, Google File System, and also MapReduce papers. Following these papers, Mr. Dow Cutting has added distributed file system support and MapReduce support to his project Nutch. And it continued for 2 years, and in around 2006 Yahoo hired Mr. Dow Cutting and they spinned off Hadoop project out of Nutch, and Hadoop was made as Apache project in 2006. And Hadoop was gaining popularity and it was used by many companies like New York Times, which generated a record of converting 4 terabytes of images over 100 node cluster. And in 2008 Facebook has launched Hive, which gave SQL support for Hadoop. Don't worry, we will be discussing Hive in detail later. Just understand that in 2008 Facebook has launched Hive support for Hadoop. And in 2008, at the end of 2008, Cloudera was founded and Dow Cutting joins Cloudera. This is a brief history of Hadoop. Earlier also you understood the core components of Hadoop. First one is HDFS, stands for Hadoop Distributed File System, which is used for storage. If you are using HDFS, the data is distributed across various data nodes, and by default in HDFS the default replication factor is 3. That means the data is natively redundant. If one of the node is down, you need not worry, the data is replicated thrice by default. And in HDFS we have a daemon called as NameNode, which maintains the metadata of all the files and the blocks in RAM. And the next core component of Hadoop is MapReduce, which is actually the programming. Whenever you are using MapReduce along with HDFS, your MapReduce program splits a task across processors. The same MapReduce job is sent to the data nodes, the nodes on which the data is residing. So once you submit a MapReduce job to Hadoop cluster, the MapReduce job is given to task tracker, and task tracker will execute the tasks on the local data. So your programming is, MapReduce program splits a task across multiple processors. Whenever you are using MapReduce, as you have already understood, the processing happens near the data and it assembles the results. The programming is executed on data which is local. We have already understood this part. And MapReduce is self-healing and high bandwidth. Can you tell me how MapReduce is self-healing? Suppose if a job is submitted, what happens? As we understood earlier, the client will submit the job to job tracker, and job tracker will pass the job to task trackers, and task trackers are the ones which are executing. When task trackers, let's assume this task tracker 2 is executing some task and suddenly it crashed. Will it result in failure of my job? No. The job tracker will choose one more task tracker to execute the same task. So it is self-healing, right? Okay, next. And MapReduce uses clustered storage. So what is a Hadoop cluster? To just define a Hadoop cluster, this is the definition. A set of machines running HDFS and MapReduce is known as Hadoop cluster. In Hadoop cluster, there are a lot of Hadoop components like NameNode, data node, task tracker, job tracker, etc. And individual machines, we call them as nodes. So a cluster can have as few as one node to as many as several thousand nodes. So in your cluster, more nodes you have in your cluster, better will be the performance. Okay. Now on top of HDFS, there are other packages which are developed. We already understood that MapReduce internally uses HDFS. Whenever you submit a MapReduce job, you submit the MapReduce job to job tracker. Job tracker will give the jobs to task trackers which are running on the slave machines. Task trackers will execute on the block of data which is stored in HDFS. So MapReduce is developed on top of HDFS. Similarly, HBase is another package or product we say which is developed on top of HDFS. HBase is a database which internally uses HDFS for its storage. And again, on top of MapReduce, there are some high level packages like Hive, Pig and Uzi. If you are a SQL developer and if you are not comfortable writing Java programs, you can go with Hive. MapReduce programming has to be done in Java. Suppose if you are not a Java programmer, you will find it difficult to write MapReduce programs. So for people like you, there is a package called as Hive which is developed on top of MapReduce. What you do is you write Hive queries which are similar to SQLs. You submit Hive queries to Hive. Hive will translate the queries to MapReduce jobs, and MapReduce jobs will be executed on your HDFS cluster. So Hive is for SQL developers. It is developed on top of MapReduce. Suppose if you are not an SQL developer and if you are good at writing some scripts, then Pig is your choice. So Pig is also developed on top of MapReduce. Whenever you write any Pig script, whenever you write any Pig command, the Pig command will be translated to MapReduce, and then MapReduce programs will be executed on HDFS. So Pig is a choice if you are a developer who is comfortable in writing scripts. We will discuss about more on Hive and Pig, when to use Hive, when to use Pig. You'll gain more understanding as we go further. We have dedicated chapters for Pig and Hive. We'll go to the internals of Pig and Hive. And what is this Woozy? Woozy is also developed on top of MapReduce. Woozy, we call it as workflow engine. What do I mean by workflow engine? So it is a very common scenario where you write multiple MapReduce jobs, job 1, job 2 and job 3. It might be a case that the output of job 1 will be input to job 2. The output of job 2 will be input to job 3. So you have some chain of jobs which has to be executed. What you can do is you can use Woozy and configure how you want your jobs to be executed, in what order and all. It is an XML based configuration. And by using this XML based configuration, you submit all your jobs to Woozy. Woozy will take care of executing all these MapReduce jobs. So we will be discussing about Woozy also in detail a little later. Okay, don't worry. As of now, I am trying to just give you a high level picture as of now. So these products which are developed on top of Hadoop are called as Hadoop Eco-System. These products like Pig, Hive and Woozy work on top of MapReduce and HDFS. So we call these products as ecosystem. Okay, coming to HDFS, you already know why HDFS. We have seen in my earlier video also, if one machine has to process 1 terabyte of data, if there are 10 machines which are processing 1 terabyte of data parallelly, then it will be more efficient, is it? So with the same idea, HDFS has been developed. In HDFS allows you to store 1 terabyte of data on multiple nodes. So processing of data can be done on multiple nodes instead of single node. So the processing of data will be fast if you are using HDFS. This we have already discussed in my earlier videos clearly with examples. So we also have discussed that there are daemons running on your cluster. On master machine there will be 3 daemons: job tracker, NameNode and secondary NameNode. These are all the 3 daemons which will be running on master node. Remember one thing, there need not be a single master, there can be 3 masters, master 1, master 2, master 3 machines. And on master 1 there can be job tracker running, on master 2 there can be NameNode running, and on master 3 there can be secondary NameNode running. Or you may decide to run job tracker and secondary NameNode on a single master and NameNode on different master. It all depends on how you configure. But speaking at a high level, these are all the 3 daemons which will be running on master node. And on slaves, what are all the daemons running? Data node and task tracker, right? So tell me which all daemons belongs to MapReduce, which daemons will be used while executing MapReduce programs? Job tracker and task tracker. Job tracker and task tracker are MapReduce daemons belonging to MapReduce engine. And what are all the daemons belonging to HDFS? NameNode, data node, secondary NameNode. These are all the daemons belonging to HDFS. You have already seen all this functionality. And also you understood this diagram earlier only. This is how a Hadoop cluster may look like. See, if you see in my cluster, I have n number of racks and in each rack I have some machines on which data node and task tracker are running. These are all slave machines. Name node is running on one machine, job tracker is running on one machine, secondary name node is running on one machine, and Hadoop client can be running on another machine. This is how a typical Hadoop cluster will look like. So as you already know, HDFS, which is nothing but Hadoop distributed file system, is responsible for storing data on the cluster, and data is split into blocks of size 64 MB by default in Hadoop 1, 128 MB by default in Hadoop 2. And also you understood that the default replication factor in Hadoop is 3. Why is replication required? To ensure reliability. That means if one of the node is down, you don't want to lose the data. To ensure reliability and availability, replication is done in HDFS. HDFS provides redundant storage for massive amount of data. So generally in HDFS what we do is, the slave machines can be low cost machines, or we say commodity hardware. So you save large amount of redundant data on commodity computers. Okay, and one very important thing you need to understand about HDFS is, files in HDFS are write ones. No random writes to files are allowed. Okay, so mostly we don't use HDFS where we need to update the data, because the data is so huge in gigabytes and terabytes. Updating files might be a costly operation. So Hadoop does not support updating of the files. If you are working on files which needs to be updated frequently, then HDFS is not suited for such files. Files in HDFS are write ones. Once you write to HDFS, you should not modify those files. Okay, so you need to remember these things. And HDFS is optimized for streaming, for large streaming reads of files. So don't use HDFS for small files. Use HDFS for large files. So, and also HDFS is good for sequential reading rather than random reads. I have a simple question. Is HDFS suited to store small files of say 1 MB, 1 MB, 1 MB? Yes, of course we can store files of size 1 MB in HDFS, but the problem is, for each file the metadata needs to be maintained in NameNode, and NameNode stores the data in RAM. So if you are storing large number of small files, the memory available for NameNode might not be sufficient. So HDFS is not good for large number of small files. It is good for small number of large files. Okay, and you already know what are the main components of HDFS. The NameNode, which actually runs on the master machine, and data nodes which run on slave machines. NameNode is responsible for storing metadata of the blocks, and data nodes are responsible for storing the data. Actual data is stored on data nodes and responsible for serving read and write requests for the clients. We have already understood about NameNode and data node, and also we understood about NameNode that it stores metadata in main memory. The entire metadata is in main memory. When I say metadata, what do I mean? The metadata may contain all the list of files which are maintained on HDFS, and for each file there might be n number of blocks. The list of blocks for each file, and also one block might be present on multiple data nodes. The list of data nodes for each block, all such information will be maintained in metadata. And also NameNode maintains the timestamps of file creations, file deletions, access time, replication factor of each file. Everything is maintained by NameNode in main memory. To give you an example of how NameNode maintains metadata and data nodes contain blocks, this is a simple example. We have seen this diagram earlier also, but quickly just to revise. Suppose if NameNode contains metadata for two files, foo.txt and bar.txt. Here is the metadata of NameNode. Foo.txt, it's containing which blocks? Block 1, 2 and 3. And block 1 is present in which nodes? Block 1 is present here, here and here. Block 2 is present here, here and here. So the information about a file comprises of what blocks, and each block is present in which data node. All such information is stored in main memory of NameNode. And data nodes hold the actual data, and each block in data node is of size 64 MB or 128 MB, and each block is replicated thrice on the cluster. And we have seen how writes happen to HDFS. At a high level, let me tell you again. Whenever you want to write a file to HDFS, you use a client program, and by using Hadoop client program, you give the file to NameNode. You give the file to Hadoop client, and Hadoop client will interact with NameNode and ask, hey, I have split my file into 3 blocks, block A, block B and block C. First tell me where shall I write block A? NameNode responds, hey, write block A in these nodes. Then the client writes the blocks directly on data nodes. So one simple thing you need to remember is, who writes the data actually into data nodes? Is it client or NameNode? NameNode does not write. NameNode will just give the client where the blocks have to be written. Okay? Client only will write the actual data to data nodes. If you see anatomy of file write, let me just tell you. Suppose I want to write a file of size, a file a.txt of size 100 MB. What the client? I'll give my file to client, Hadoop client. Client will break this 100 MB file into block 1 of size 64 MB and the block 2 of size 34 MB. Then it will ask the NameNode, hey, create metadata for block 1. NameNode responds to the client saying block 1 can be written in some data nodes like data node 1, data node 2 and data node 3. Now what the client will do is, client will write to first node only, data node 1. Client will send packages to data node 1. Data node 1 will take responsibility to write the block to data node 2, and data node 2 will take the responsibility to write the data to data node 3. Then the acknowledgements will be sent back to the client. So remember one thing, if the replication factor is 3, client will not write the same block to 3 nodes. Client will actually write a block to first data node only. Then that data node will take care to replicate the block into another data node, then this will take care to replicate the data to another data node. That's how it works. Okay, keep this in mind. Next, coming to the internals of how it actually works. See this diagram. I want to store file.txt. First, what the client will do is client will contact NameNode and ask the NameNode, hey, I want to write block A to the cluster. Give me the data nodes where I can write. Let's say the data NameNode says write the data to 1, 5 and 6 nodes. So first, once the client gets a response, what the client will do is client will ask the data node 1 to get 5 and 6 ready. Data node 1 will ask data node 5 to get data node 6 ready, and data node 6 will become ready. Once data node 6 is ready, it will send an acknowledgement to 5. 5 will send acknowledgement to 1. 1 will give the response to client saying that okay, I am ready. Okay. So now the data nodes are ready. Then the client will start writing the data to data node 1. Afterwards, data node 1 will write it to data node 5. Then data node 5 will write it to data node 6. That's how the writes will happen. And one more thing I would like to tell, whenever NameNode is responding with the blocks, the data nodes where the block can be stored, the NameNode is rack aware. That means it will select one data node from one rack and two data nodes from another rack. It will not give the data nodes belonging to same rack. It will try to find the data nodes belonging to different racks and then give the response to the client. So we say that NameNode is rack aware. We already discussed about rack awareness. If NameNode is not rack aware, it might happen that all the data nodes to which we are writing might be present in single rack. If the whole rack goes down, my data is lost. So to avoid such scenarios, NameNode executes something called as rack awareness script, which will tell to NameNode which data nodes are present in which racks. Then the NameNode will select data nodes belonging to different racks. Okay, that's how the NameNode will decide which data nodes to write to. Okay, now you understood the flow. Let me just tell the flow again. Whenever we want to write file.txt, we give the file.txt to client. Client will split my file into blocks and it will pick the first block. It will ask the NameNode, hey, I want to write block A. Tell me in which data nodes to write block A. NameNode internally executes rack awareness script, which will tell which data nodes are present in which racks. NameNode picks the data nodes belonging to different racks. That means it will pick one data node from a rack and another two from another rack, and then give the data node names to the client. Then the client, what it will do is the client program will ask the first data node to ready data nodes 5 and 6. This data node 1 will ask the data node 5 to ready 6. And once data node 6 is ready, it will give acknowledgement to 5. 5 will give acknowledgement to 1. 1 will give acknowledgement to client. Now the data nodes are ready to accept the writes. Then the client will actually write to data node 1. Data node 1 will write to data node 5. Data node 5 will write to data node 6. That's how writes are pipelined among the data nodes. And how do data nodes communicate with each other? Through which port? 50010. Okay. So in my earlier presentation also, if you remember, I told you how to configure this TCP port. By default, if you don't configure any TCP port, the data nodes will communicate to TCP port 50010. Okay, now the writes have been done. Once writes have been done, the acknowledgements will go to NameNode asynchronously. And NameNode, once it gets acknowledgement, it will write such data, such metadata in the memory. And finally, the client gets success. The client gets success once writing is done to data node 1. Client will not wait until the data is replicated to 2 and 3. Once client is successful in writing data to data node 1, he will get success. Then asynchronously, data node 1 is responsible to write data to data node 2. Data node 2 is responsible to write to 3, and once writes are successful, these data nodes will send acknowledgement to name nodes as part of their heartbeats. Okay, that's how the write notification occurs. And if a file is containing multiple blocks are replicated along the whole cluster. So if you are storing 1 terabyte file, you require 3 terabyte storage and 3 terabyte network traffic. Okay, and also understand that one file will span over the whole cluster. The more the number of blocks of a file, the more it is widespread. Okay, then coming to data node and name node interaction. Data node, as we discussed earlier, will send heartbeats to name node at some regular interval, and every 10th heartbeat is a block report which says I am containing these blocks. Name node, once it gets this heartbeat, it will extract the data from heartbeat and then will update the metadata accordingly. So heartbeat will be sent every 3 seconds. Okay, we already understood about a scenario where a particular data node is down. Once a particular data node is down, what happens? The heartbeat will not be received by name node, and name node will replicate the data present in this data node. But what if what if name node is down? Name node is a single point of failure in Hadoop 1.x. If name node is down, the whole cluster is down. We cannot do anything on the cluster. So the same thing whatever I discussed here, missing heartbeats from a data node signifies the loss of nodes. Name node will check. Suppose if there is no heartbeat from data node 3, name node will check in the metadata. Data node 3 is containing what all blocks? A and C. It will try to re-replicate these blocks in other nodes by running rack awareness script internally. So a name node will take care of making sure that the replication factor is maintained. And whenever a client wants to read the file from HDFS, what happens? Assume a scenario where a file contains block A, block C, and block A, block B, and block C. Block A is present in 1, 5, and 6 data nodes. Block B is present in data nodes 8 and 1 and 2. Block C is present in 5, 8, and 9. The client will first consult the name node and ask, hey, I want the blocks of my file. Give me the blocks. The name node will return all the block locations, and what the client will do is, client will get the first nodes. What are the first ones among all? 1, 8 and 5. 1, 8 and 5. So client program will read the blocks accordingly and will get the data. Okay. Client reads the blocks sequentially. 1 first, then 8, then 5. Client picks the first data node for each block. See, block B is present in 8, 1 and 12, but it will pick the first block only. Okay. So few more things on HDFS. NameNode daemon must be running at all times. If NameNode stops, the whole cluster is down. The cluster becomes inaccessible. You need to make sure that the NameNode is running all the times and the NameNode hardware is reliable. So don't use commodity hardware for NameNodes. For data nodes you can use commodity hardware, but NameNodes should have a reliable hardware. NameNode will hold all of its metadata in RAM for fast access. Okay. And it keeps the record of changes on disk for crash recovery. We will discuss about this thing in my next videos. And although the files are split into 64 MB or 128 MB blocks, if a file is smaller than this, the full 64 or 128 MB is not used. That means if a block size is say 40 MB, 24 MB is not wasted. It will occupy only 40 MB only. You need not worry. And where are the blocks stored? Blocks are stored as standard files on slave nodes, on where data node daemons are running, in a directory specified in dfs.data.dir in HDFS site.xml. In my earlier video, when I was configuring my cluster, I showed you the configuration of HDFS site and I configured this property. Just go and look inside your installation and what is this property pointing to? This directory, whatever value we have configured, that is the location in which my data files are stored. Okay. And without metadata on the name node, there is no way to access the files. So if name node is down, the whole cluster is inaccessible, it's waste. So these are the HDFS basics. Most of the things in this presentation are already known to you, and we learnt some more basics. Catch you in next video.